So this is section 3 for day 2, and we started out with day 1 talking about motion. And so for day 2, we're going to still talk about motion, but as long as we're talking about motion, we're going to talk a little more about physics. And we're really going to focus on gravitational motion. So we're going to talk about free fall. And so if we take a look at the gravitational constants for accelerational gravitation, the acceleration due to gravity, you're probably most familiar with this number, 9.8 meters per second squared. And that's the metric value. And then the English value is 32 feet per second squared. And here's the value in centimeters as well. Just kind of keep in mind the biggest differences between calculus and physics and how we work with these numbers is sometimes in physics, first of all, in calculus, I mean, we tend to use the feet per second squared, so the 32 instead of 9.8. We also tend to look at free fall equations as positive being downwards. So we have to kind of take a look at that scenario as well. So the position equation for free fall is half gt. Now, really, there's some other terms over here, like a VOT and a S initial or initial position, but what we're assuming is that we're dropping something in that it's at rest, and we're calling the beginning spot 0, and down positive. So we kind of boil it down to half gt. And if we use our higher order derivatives and take the derivative of this, we're going to get velocity. So before we do that, we'll put in the value for g, which is 32. So our position is 16t squared. And then when we differentiate position to get velocity, that the s prime of t is doing the power rule on this, which brings down the 2. So we get 32t. And then we take the derivative again to get the second derivative of position, or the first derivative of velocity, and that's our acceleration. So taking the derivative of this ends up being 32. So just to keep in mind that velocity is the derivative of position, and acceleration is the derivative of velocity. So this is your progression of higher order derivatives that we've been talking about for the last few days. The units of motion then, if we take a look at this, velocity is measured in feet per second. And that's that instantaneous rate of change of position with respect to time. And acceleration is feet per second squared. Some people call this feet per second because it's the rate of change of velocity with respect to time. So let's take a look at this example. We're gonna blast some dynamite, and it's gonna shoot a heavy rock or propel a heavy rock straight up with a launch velocity of 160 feet per second. And it reaches a height of, and so if we look at this function here of the position, since we're launching something upward, and after it leaves the ground, it's only under the effects of gravity, so it's technically considered free fall, even though it's moving up at the beginning. And so we see the initial velocity here of 160. So it's the initial velocity times t minus the half the acceleration, so 16t squared. So this is where we have a positive or an upward initial velocity, and then we actually attach the negative sign now to the gravitational acceleration because it's pulling the rock, it's attempting to pull the rock down. So we're going to look at these questions here. So let's take a look at this first one. How long does it take for the rock to reach its highest point? So in looking at what we're talking about here, here's the path that the rock takes, and the highest point is right here. So we want to know how many seconds it takes to get to this point right there. And so if we think about this in terms of calculus, then that is the vertex of the parabola, and we know that the tangent line is horizontal there. In other words, the steepness of the graph, the steepness of the function is 0. That's where we got a flat horizontal tangent line. So if we take the derivative of this position function and set it equal to 0, that is telling us that's providing that how many seconds it takes for the velocity to be 0, or the tangent line to this position function to be 0. So the derivative is 160 minus 32t. We're going to set that equal to 0, and we're going to solve this. So taking the 32t to the other side, and then dividing by 32, it must take us 5 seconds for the rock to get to that point. And so the next question is, how high does the rock go? So before we jump into that question, you might, some physical properties of this whole scenario you might be thinking about is, well, if it takes us 5 seconds to get up to the top, then it must take us 5 more seconds to get back down to the bottom. And so, we're going to recognize this asymmetry in the parabola and use that in our favor. So how high is the rock go? So we want to know this elevation here. And so really what we want to know is the position at 5 seconds. So when we stick 5 back into this position equation, we get an elevation of 400 feet. It's 800 minus 400. So it's an elevation of 400 feet. And for part C, it says, what is the velocity and the speed of the rock when it's 256 feet in the air? So if we look at, again, the path of the rock here, 250 feet, if the top here is 400, then 250 feet must be about here. So if we notice where my arrow is, we cross that twice. So if that's where 256 is, then what we can do is we can take the position equation and set it equal to 256. And we can solve this equation for time. So when I move everything over to the left, I get 16t squared minus 160t plus 256. I know I'm going to get 2 points in time here where my velocity is, or where my rock is 256 feet off the ground. So I'm going to factor out a 16 here. And when I do that, I'm left with t squared minus 10t plus 16. So I got to think of what multiplies to 16 and adds to negative 10. And that is negative 8 and negative 2. So our time must be at 8 seconds and at 2 seconds when we're this high, when we're at this elevation. So, so if we look at then after 2 seconds, so we want to know the velocity at these locations. So we need to take that derivative that we found earlier in the problem, and now we can plug in our 2. So our velocity when we're right there at 2 seconds is 160 minus 64, so that looks like 96 feet per second upward. And so we're going to use our symmetry again. If we're going 96 feet per second upward at this elevation, then the same elevation on the other side, we must be going 96 feet per second downward. And so at that location, we're going 96 feet per second downward. And you can find that either by using symmetry or by plugging in the 8. That'll get you also minus 96. And then in terms of the speed, we know the speed is the absolute value of velocity. So we're going to look at these values and we're just going to make them positive. So looking at this value, making it positive just means keeping the value 96 feet per second. Looking at this value, making it positive means keeping 96 feet per second. So if we had a radar gun and we could point it at the rock, the radar gun would read 96. For part D, it says, what's the acceleration of the rock at any time during its flight? This is one where you could almost not do any work because you know the acceleration is twice this value. But if you wanted to show some work, really what we're saying is what is the derivative of the velocity? That's what the acceleration is. So we take our velocity function. We could also ask it as what is the second derivative of position. We take our velocity function. Here's our velocity function, and we differentiate it. So when we differentiate this, we get minus 32. And so our acceleration, notice this is a constant because acceleration of an object close to the Earth's surface is a constant. And so it's minus 32 feet per second squared. So the minus sign is saying it's accelerating downward. at 32 feet per second for every second of travel. For part E, it's another one where you might not have to show too much work. It says how long does it take for the rock to hit the ground. So we want to know how long it takes to get its position back to 0. So we could set the position function equal to 0 and solve this. So we would solve it by factoring out a 16t, and then we would set each equal to 0. So we get a t values of 0 and 10 that make this a 0. So if we think about this, we get two answers. The first answer, t equals 0 seconds, is at the beginning. So in other words, all that's saying is that at the beginning, when we start collecting data, our rock is at the ground. Then we blast our dynamite. This rock goes into the air and falls back down to the ground 10 seconds later. And you really could have gotten that answer just by going back to part, which part is that? It was either part A or B where we found that it took 5 seconds to get to the highest point. So if it's going to take 5 seconds to get to the highest point, it's going to take another 5 seconds to get back down to the ground, back to that same elevation. Another application of a rate of change is something we call flow rate or a fill rate if you're filling up a tank. So this is kind of a common question where you're being asked to either drain or fill a tank. So in this case, the tank is draining. And it's draining according to this function. And so if you think about, we fill up a tank and we get it full of water, and then we kind of pull a plug at the bottom and the water drains out. So we're looking at how that water is draining out. So the first question, A, is what's the capacity of the tank? All capacity means is how much liquid fills the tank. So we know that the tank is full at the beginning. The beginning means time is equal to 0. So we're being asked to find Q, the capacity at 0. So when we plug in 0 here, we can find that capacity. The 0 take away 10 is -10. Squaring -10 is a positive 100. And so times 75 is 7,500 gallons. So there's the capacity of our tank. Not any calculus involved there. For part B, so I put a dot on the graph here to show our capacity when we started, and then as we release that hole, the tank starts to drain until it's empty. And so for B, it says how fast is the water running out at 7 minutes? So 7 minutes is about right here. And so we want to know that how fast is the velocity. And so we want to know the velocity right there at 7 minutes. So, so we need to find that velocity. So in order to find the velocity, we have to take our capacity and differentiate it. We need the rate of change of the capacity of the tank. So, so we're going to take the derivative of this. It's just that taking the derivative of this means we have to FOIL this out. So when I'm saying derivative, hopefully you're thinking slope right now. When we find a value, it's going to be the steepness of this curve right here, or the slope of the tangent line. So we're going to FOIL this out. That's 75 times t squared minus 20t plus 100. We're going to distribute the 75, and then we're going to go ahead now. We can differentiate by using the power rule. So q prime then is 150t. That's the derivative of this. Minus 1500 plus 0. The derivative of this last term is 0. So we're going to just drop that, and we know this is our flow rate. And our flow rate is the same thing as the velocity of our water running out. So when t is equal to 7, I can put a 7 in here, and I see that our flow rate is negative 450 gallons per minute. So the negative sign means that the water is flowing out, and we're losing a 450 gallons for every minute that we allow that water to run. But the term how fast is really a speed, which means we should be taking the absolute value of that. So the actual speed, knowing that it is running out is kind of the negative indicator right here. The actual speed is just 450 gallons per minute. For part C, it says, what is the average rate at which the water flows out during the first 7 minutes? So whenever we see the word average, we have to kind of heighten our awareness here. Average rate means algebra slope. Remember we've got 3 words that mean slope. The word slope itself, the word derivative, and the word rate. So we have to look at this anytime we see the word average. We got to stop and think here. Am I being asked to do calculus or algebra? So average rate is algebra slope. So the tricky part is that we need, if we're going to calculate the slope, that means we're going to calculate the slope between 2 points on this curve. And this curve is the capacity curve. So it's a secant line of this capacity curve. So with our algebra slope, then we need our 2 points. So there's our 2 points. The first 7 minutes means from time equals 0 to time equals 7. So we want the slope of this line here. Okay, and what that means is that we need the x and the y coordinates of these 2 points on the function. So this first point here, the time is equal to 0, and the y value is equal to 7,500. And the second one are the x and the y coordinates here. So we know the x equals 7, and the y is going to equal whatever we get here. So it's going to be 75 times 3 squared, which is 75. Actually, negative 3 squared, but negative 3 squared is 9. So 75 times 9, which is 675 gallons. Now we can do our algebra slope. So our algebra slope then is going to be Q7 minus Q0 over 7 minus 0. So it's our rise over our run. So we're going to have 675 minus 7,500 over 7. And when we do the math there, we get an average rate of 975 gallons per minute. It's negative because it's sloping downward. So if we compare that to our tangent line, we see that I should have left the tangent line in here, but the tangent line is much flatter. Remember, the tangent value was negative 475, I believe. So, or was it negative 450? One of those two values. So it's much steeper, that average rate. And for part D, it says, how long does it take the tank to empty? I would argue that you probably don't have to do much math here. Getting this tank to be empty means I have 0 capacity, and we can read that right off the graph. It takes 10 seconds. Algebraically, it just means we're going right down there to that location where the capacity is 0. So then, and all that means is Q of t is 0. So if Q of t equals 0, then we need to solve this for the zeros. And so in doing that, we can divide the 75 out, and we get t minus 10 squared, quantity squared equals 0, and we know that is 0 when t is 10. So we know it takes 10 minutes to drain that tank. So just kind of to summarize the velocity, speed, and rates of change. Rates of change, that's another way of saying instantaneous, an instantaneous rate. And if it's instantaneous, then it's the first derivative. So in terms of motion, we have rates of change represent velocity and acceleration. So velocity is the rate of change of position with respect to time, and acceleration is the rate of change of velocity with respect to time. In terms of flow rates, we can represent fluid flow or fluid motion by taking the derivative of the capacity function. And then something that's not mentioned here, but from day one, we also know that instantaneous rate of change we can take, like we can take the instantaneous rate of change of area with respect to radius. It doesn't always have to be with respect to time. So at this point, you should be able to do day 2 of the homework from 3-4 and finish up section 3-4.